Good day, esteemed researchers and curious minds tuning in from around the globe. We're here to delve into the fascinating world of large language models, specifically how we can make them better and faster. Our focus is the groundbreaking paper, Better and Faster Large Language Models via Multi-Token Prediction. This research challenges the status quo, proposing a more efficient approach to training these models, with significant implications for their performance and speed. So, let's embark on this journey to explore how we can push the boundaries of what's possible with large language models. Stay tuned. Our research is driven by the motivation to enhance the efficiency of large language models, or LLMs. We've observed that the existing approach of next token prediction, while impressive, has its limitations. It tends to focus on local patterns, often overlooking more complex, hard decisions. This inefficiency is evident when we compare it to the learning capabilities of human children. Despite the vast amounts of data fed into these models, they still require significantly more input than a child to achieve the same level of fluency. To address this, we propose a new architecture based on multi-token prediction. This approach not only aims to improve the efficiency of LLMs, but also seeks to address the issues associated with the next token prediction method. By predicting multiple tokens at once, we believe we can make better use of computational resources and data, leading to more effective and efficient language models. In essence, our problem statement revolves around the inefficiencies of the next token prediction approach, and our proposed solution is the multi-token prediction architecture. This is a step towards creating more powerful and faster transformer models. Our research introduces a novel method, the multi-token prediction architecture. This innovative approach predicts multiple future tokens simultaneously, all in parallel, without any additional training time or memory overhead. Turning to our evaluation and results, we tested this method on natural language, summarization, and natural language mathematics benchmarks. The results were promising. Multi-token prediction models, specifically with n equals 2 and 4, showed improvement over the next token baseline in RUGE-LF1 scores. Interestingly, we observed that the performance gap between the multi-token prediction models and the next token baseline decreases as the dataset size increases. These findings suggest that our multi-token prediction method is not only effective, but also scalable, offering potential for further exploration and application in the field of language model training. Let's delve into the heart of our study. We're focusing on large language models, or LLMs, which currently rely heavily on next token prediction. This method, while effective, is not the most efficient way to acquire language, world knowledge, and reasoning capabilities. Our goal is to enhance the efficiency of these models, both in terms of computation and data usage. This not only improves their performance, but also reduces their ecological impact. Now, take a look at the figure on the right. It provides an overview of our proposed solution, multi-token prediction. This approach allows the model to predict multiple future tokens at once, making it more efficient and effective. We believe this is a significant step forward in the development of LLMs. The crux of the problem we're addressing is that next token prediction, while impressive, tends to overlook hard decisions and requires significantly more data than a human child to achieve language fluency. This inefficiency impacts not only the speed and accuracy of large language models, but also their ecological footprint. Despite its achievements, next token prediction tends to latch onto local patterns, often missing the bigger picture. Our proposed solution to this problem is a multi-token prediction architecture. This approach doesn't increase training time or memory overhead, and it allows the model to predict multiple future tokens at once. This method is a significant departure from the traditional next token prediction, and we believe it holds great promise for improving the efficiency and effectiveness of language models. Our research introduces a novel approach to language model training, where we evaluate multi-token prediction on natural language, summarization, and natural language mathematics benchmarks. We've trained models on massive datasets, specifically 200 billion and 500 billion tokens. This approach is a departure from the traditional next token prediction method, aiming to improve efficiency and performance. We believe that by predicting multiple tokens at once, we can drive these models towards better sample efficiency, ultimately leading to stronger and faster transformer models. This could potentially revolutionize the way we train language models, making them more effective and efficient. Our research introduces a novel approach called multi-token prediction, designed to enhance the efficiency of large language models, or LLMs. This method is unique in its ability to predict multiple future tokens simultaneously, a significant departure from traditional methods. Current techniques, such as next token prediction, have shown limitations. They are inefficient and require significantly more data to achieve fluency compared to human learning. Multi-token prediction addresses these issues head-on. It predicts n future tokens from each position in the training data, executing all predictions at once and in parallel. This approach not only streamlines the prediction process, but also enhances the overall efficiency of language model training. In essence, multi-token prediction is a promising step towards creating more powerful and faster transformer models. It's a simple yet effective modification that we believe will significantly improve the performance, coherence, and reasoning abilities of LLMs. In our research, we've trained models on a massive scale, using 200 billion and 500 billion tokens. We've employed a variety of prediction losses, including 4-token, 2-token, and next token, to optimize the learning process. Our architecture is designed for efficiency and effectiveness. It features a shared transformer trunk and independent output heads, all tied together with a shared unembedding matrix. This structure allows for simultaneous prediction of multiple tokens, enhancing the model's performance. Moreover, we've implemented a memory-efficient approach. We've adapted the sequence of operations to minimize GPU memory utilization, ensuring our model is not only powerful, but also practical. In essence, our research proposes a novel, efficient, and effective way to train large language models, pushing the boundaries of what's possible in the field of AI. Our research introduces a novel approach to language model training, focusing on multi-token prediction. This technique allows the model to predict multiple future tokens simultaneously, enhancing its efficiency. In the inference process, we primarily use the next token prediction head for auto-regressive prediction. However, we also employ additional output heads to expedite the decoding process. The benefits of multi-token prediction are manifold. Notably, it enables self-speculative decoding, which can make models up to 3 times faster at inference time. This speed increase can significantly enhance the practicality of these models in real-world applications. Our experimental design is robust and comprehensive. We evaluated our approach on natural language, summarization, and natural language mathematics benchmarks. These diverse tests provide a well-rounded assessment of our model's capabilities and potential. In summary, our research proposes a simple yet effective modification to language model training, with promising results that could revolutionize the field. Our results in Section 2 have significant implications. Firstly, the improved performance of multi-token prediction models showcases their effectiveness in training stronger and faster transformer models. This is a promising step towards more efficient language learning. Secondly, we observed a reduction in the performance gap with larger dataset sizes, suggesting that multi-token prediction models scale effectively. This scalability is crucial for handling the vast amounts of data in real-world applications. Furthermore, we found an increase in the capability to solve code problems, enhancing the practical utility of large language models. This means our models can be more useful in tasks that require complex problem-solving skills. Lastly, we saw an acceleration of inference time across a wide range of batch sizes. This demonstrates the efficiency of multi-token prediction in improving the operational speed of LLMs, making them faster and more responsive. In summary, our findings indicate that multi-token prediction can significantly enhance the performance, scalability, and efficiency of large language models. Let's take a look at the performance of multi-token prediction models on abstractive text summarization. These models were trained on 200 billion and 500 billion tokens of natural language and evaluated on 8 summarization benchmarks. The results, as you can see in the figure, are quite impressive. Both the 2-token and 4-token prediction models outperform the next token prediction models, demonstrating the effectiveness of the multi-token prediction approach. Now, let's highlight the key contributions of this approach. Firstly, we introduced a simple and efficient multi-token prediction architecture. Secondly, we provided evidence of the benefits of this approach at scale, with models solving more code problems. Lastly, this approach enables self-speculative decoding, which makes models faster at inference time. These contributions pave the way for stronger and faster transformer models, and we hope they inspire further research in this area. Our research has led us to some key takeaways. Firstly, we found that multi-token prediction can train stronger and faster transformer models. This approach is particularly beneficial at scale, solving more code problems on average. Additionally, it speeds up models at inference time across a variety of batch sizes. Interestingly, as the dataset size increases, the performance gap between multi-token and next-token prediction models decreases. This finding encourages us to explore novel auxiliary losses for large language models. In conclusion, our work opens up new avenues for improving the performance, coherence, and reasoning abilities of these fascinating models.